So the project, with the benefit of hindsight, looked at past pest incursions and asked the question about whether good decisions were made. And I found this quote from a book about animal biosecurity, and I suppose I found it towards the end of the project, which perhaps was unfortunate, but this was, I suppose, what we tried to do. So one can, with hindsight, perceive alternative paths and argue that one not followed would have been better. Sometimes the alternatives were clearly seen at the time, but often were not. We attempt to explain how the conflicts played out and how the choices were made. So it's perhaps easy to see with hindsight that something could have been done better, but what we tried to do was to say, well, if we take the information that was available at the time, were good decisions made, or were perhaps not so good decisions made? This question of optimal incursion responses I describe as really a wicked problem with no easy solution. I think David Stern used this phrasing when he was describing climate change. So it's a really difficult problem to address. And I think one of the key issues is really about the economics of information, because as an incursion is unfolding, then information is generated all the time, and to actually address this, you have to anticipate that information is going to be generated, so that your decisions might change as you're going through. And so what you have with an incursion is actually a value of information, a value of a discovery of a pest sooner rather than later. But that value of information depends on what actions can flow from it. So if there's no incursion response, then the value of information of knowing a pest is somewhere is actually zero. So the value of information depends on the state of the pest incursion at the time of detection. And if there's a very small number of pests, then locate a very small population, then locating the pest is really valuable because something can be done. If they're everywhere, then the value of that information is actually quite small. Intrinsically, the state of an incursion, say a biosecurity system, is difficult to determine because information is pretty well always partial, it's spatial, and it's dynamic, or it's changing. And as Kylie mentioned, often data is poor, and we found throughout this project, even for known incursions, that actually the data is quite poor. So we had a big challenge. We're claiming that we're one of the first economic studies to measure the value of information during an incursion and incorporate it into a risk analysis. The approach that we were using was to develop a pest simulation model, which was for actual incursions, define a policy set, eradication technique, extent, active surveillance and its extent. We compared the costs of thousands of simulated incursions, and then we identified approximately the optimal policy. And I say approximately because that's you can usually identify some policies that are really bad, but there might be a lot of close ties with other policies. So that was an outcome. So I'd just like to run through some results. So these were our list of 4 least wanted. So the Capra beetle, potato in WA, potato cyst nematode in Victoria, Asiatic citrus canker in Queensland, and great phylloxera in the Yarra Valley of And with each of these pests, we've tried as far as possible to develop a common approach to the pest modelling and to the economics. And one thing that was apparent as we were going through this is the key importance of technology. So technology determines what's possible, but it also determines costs. And it's also something that's shifting through time, because as new technologies become available, some of the things we're hearing about today, then that changes the costs. It means different things are possible. Eradications can be attempted where they possibly weren't previously. So Capra beetle arrived. I should not do that. I've just saved you the whole presentation there. Oh, that's the light. So Capra beetle arrived from Scotland via possibly Pakistan to a house in Perth. Was discovered by passive surveillance fairly quickly. Householders recognised there were beetles everywhere. The eradication response was to wrap the house in plastic. We identified the surrounding metropolitan area as a possible target zone, so that was up to 500 metres. From this and from what DAFWA did, we got the information mainly from Rob Emery of DAFWA. Then there was a range of surveillance strategies, and so that involved different types of traps. That was the technology, and the other variable was the frequency with which traps were visited and the area over which the traps were deployed. And so we identified a range of surveillance intensity from one, which was the most sophisticated traps, through to passive surveillance, which is where householders were just looking for beetles and occasionally finding beetles. Attached costs to all that. Surveillance, what were the main parameters? It was the extent of surveillance, so what is the surveillance cut-off? How many houses are you going to do surveillance in? And that has a cost implication. How long are you going to do surveillance on those houses? Are you going to maintain a high level of surveillance throughout the time, or is there going to be a gradual reduction in the intensity of surveillance? So these were parameters we took into account. Precautionary surveillance is obviously where you're looking at properties that haven't had any detections. Precautionary eradication, obviously in this case the beetles were eradicated from the house by wrapping in plastic and fumigating, but you could actually have precautionary eradication, which is important for some pests, which is where you actually wrap a house that hasn't had any detections in plastic and fumigate that and really upset the residents, which is an issue we'll talk about a bit later. Closure for these types of models. Obviously no one really cares about Capra beetle in a house in Scarborough because the economic costs are quite small, easy to eradicate. The reason that there was a significant response to this problem is that you have to close the model off with some idea about the possible spread of this pest to a wider industry. So we chose the Kwinana zone and all the farms and grain stores within the Kwinana zone as a possible destination for Capra beetle after they'd settled in Perth. So that's what we call the sort of spatial closure of the model. And this is where the big costs are generated. So you work out, what are the potential costs of the rare events where the beetle spread from Perth to the grain industry. And then we developed ways of representing the results. So we did this as a risk analysis, so we identified that in this case, wrap the house in plastic and spray was the most effective policy, so that's had the lowest average cost. We then identified the extent of these policies, so we worked out what was going to be done. Eradication cut-off, it was only the house, so we weren't pestering the neighbours by wrapping their houses in plastic. Surveillance intensity, that was about the cost of surveillance. Surveillance cut-off, it was around 10 houses, and surveillance stand-down rate, that was the rate at which the frequency of revisiting the houses was reduced. So there was talking by Johan, I think, about standards of acceptable risk. Every policy or every incursion, every eradication attempt is risky, and this is how we measure the risk of an incursion. We represent it by the cumulative probability of costs. So in this case, the two policies of spray only and spray and wrap had a cumulative distribution that looked like this. So most of the results around the average, with a few extreme results. If there was any delay in detection, any failures of passive surveillance, then that would push the costs out much larger. So there was a significant probability of costs of around about $300 million. Okay, so moving on to potato cyst nematode. So that is now established in Victoria. Again, we identified different surveillance technologies, from extremely expensive surveillance through to passive surveillance, which is based on the state of the crop. We looked at precautionary eradication. We assumed that the farm itself, where the detection occurred, would have the potato crop removed and would stop growing potatoes. And then you could have precautionary eradication, where potatoes were destroyed and the crop was destroyed. Were destroyed around a larger area without detection, and then you have precautionary surveillance, where there's no pest found in a wider area. Again, the same kind of analysis. So we compared that with no control, and so the costs of no control are much higher. And then all these other active activities where the potato crop is removed tend to have lower costs. Asiatic citrus canker. So this was found in emerald, and there was the possibility of the incursion spreading to other citrus areas. So that was why there was such an aggressive response. This incursion showed the importance of passive surveillance. There was evidence that the pest had been ignored for quite some time, and actually had the pest been detected earlier, then our simulation showed that the costs of the incursion could have been reduced to about 25% of the costs actually simulated in our model. Great phylloxera. Briefly, the conclusion for the simulation there was that because there's no clear control options for great phylloxera, then it was actually optimal to probably do nothing. So just to run through some conclusions from the case studies. Capra beetle, you would pretty well always eradicate. PCN has been eradicated in Western Australia, and it could be actually contained much more aggressively in Victoria, if that was the choice of the industry. Great phylloxera, unclear, weak case for more active containment, but it depends to an extent on how you measure your spillover costs. ACC usually eradicate, especially in regions like Emerald where it's easy to contain. Future, just briefly. My interest has now switched to trying to understand incentives for biosecurity management and active biosecurity management, and also to understand why, from the experimental work we've actually done with students, why free riding is so prevalent in terms of providing simulated biosecurity efforts. So I think that's an area of great interest in the future. What should biosecurity contracts look like, and how do we provide incentives and perhaps disincentives for various types of behaviour? Okay.